All right, I think we can begin now. So welcome to week 15 of AI504. So this will be the last week of regular schedule. So today we're going to talk about image text multimodal learning as written here. And then this Thursday, there will be the final practice session. And the next week, it'll be an off week because of the final, it's a finals week. So you can focus on your projects. The question, oh, it's not quite some comment from the TA. Thank you for correcting. All right, as I said, off week next week, so you can focus on the projects. So this will be your final week for the regular class and practice. So there's a lot to tell, especially in the image text domain, but we can't go over them all in detail because there are so many. So we'll mostly focus on the very basic stuff because as in the beginning of the class, we talked about how we're going to focus on the fundamental stuff and how you can code them, how you can implement them. And then maybe you can build on top of that to do more advanced research. So today we're going to talk about the very simple stuff. I mean, we're going to go into detail only on the very simple stuff, show and tell and show, attend and tell, which all came out in 2015, actually. Then the next one is the text condition again. This actually came out in 2016, so it's a bit old, but we're not going to go into detail. In the Thursday practice session, you guys will be implementing this, show, attend, and tell. So please pay attention to this especially. All the others, they are mostly for introduction. So you can get more familiar with what things are, how things are happening in the vision and text domain these days. Especially, we're going to touch upon the DALL-E 2 as well. We've all spend some time on diffusion models, so it will be a waste if we don't talk about DALL-E 2, at least in some high level like in description. The second attendance absence will begin, I think, after this practice session, which will be when it's what date is it now? So yeah, maybe from the 9th. So next week will be mostly claims. You can talk about your attendance claims to the TA. All right, moving on. So we'll talk about image captioning first. Image captioning. So the very first thing, image to text. So sequence, we can think about sequence to sequence as a text in and text out, right? So we can think about translation where you translate English to French is sequence to sequence. So you put English in and then you have the French out, or vice versa, using an encoder-decoder architecture. Image to sequence, it's a bit different. So you have image in and text out. So you can talk about, you can see the comparison here. So there's image in and text out. So then obviously the objective would be to describe a given image in text. So it's called image captioning. So for example, we are supposed to make something like that. We're supposed to implement something like this. So given an image, this would be an image. We want to write something like this. Well, I mean, we want the model to generate captions automatically. So a person riding a motorcycle on a dirt road, they are all different examples. And they're actually working examples. So how do we do it? In sequence to sequence, obviously, we already talked about RNN using RNN for building sequence-to-sequence models, or we can use transformers to build sequence-to-sequence models. So we've covered both of them. So it could be RNN and RNN, or it could be transformer, and transformer here. Could be, you could have whatever you want. In image to sequence, obviously, what would our choices be? So the encoder, we want the image to go into the encoder, and the text to come out from the decoder. So the obvious choice would be using CNN for the encoder and RNN for the decoder. Or this could be also replaced with transformer. With the mask self-attention, obviously, so transformer. And obviously encoder, we could use like more advanced or more gigantic models like VIT, vision transformer. But this is all back in 2014, 2015. So we're going to focus mostly on the simple architectures like this. All right, so the very first one, show and tell. This came out in 2015, so it's pretty old now. It's pretty some time ago. The first paper to perform neural image captioning without any domain knowledge. So before, if we had to do image captioning, we needed some kind of like object detector or some language model or something like that. But here, there's no domain knowledge whatsoever. There's no object detection, no language modeling, no description templates. It's not retrieval based. You actually put a pixel based image in, and a text will come out. So yeah, no text ranking, it's pure generation, and it is end-to-end training. So imagine the surprise that people would have felt or experienced back in 2015 to see that this is actually possible. Like, because in 2015 this would have been a very complex test. Even like image classification was not completely solved. The ResNet came out in 2015, I think. So back then, back in 2015, image classification was still a thing, but then to do image captioning without any domain knowledge would have been a very challenging concept. But then people like this actually show that it is doable. So it's like a very it was a big hit back in the day. And I also felt like when I was a PhD student, I also felt like, is this even possible? There was a lot of surprise. All right, so the architecture is super simple. In today's standards, it's very simple. It's you have image going in to the encoder, some CNN model, and then you have an RNN hooked up to the encoder, and then the RNN generates a sequence of text, and that's it. So the very first architecture looks like this. So there's an image encoder. There's an image encoder. So image goes into the encoder. This is an encoder, and this is Inception. I think it was Inception version 1 or 2. And then based on the encoded image, there's a image representation vector at the top, right? There should be an image embedding, and then you feed that into your LSTM RNN, and then based on that, you start sampling captions one word at a time. One word at a time. So yeah, oh, it's here. Yeah, so the image encoder is Inception version 1, pre-trained on ImageNet. So it's not even version 2 or version 3. So it's version 1, the very first. I forgot the covariance shift paper, the batch norm paper. I'm sure. And yeah, text decoder is simple LSTM. So the architecture is super simple, and the equations would be also very simple, actually. So each SI being the token, or actually there were words. There were no subwords back then, so it's words. So each SI is predicted based on PI. PI, you can think of PI as a hidden layer from LSTM, or like a memory from LSTM. Or if you're using GRU, it could be a hidden layer from GRU. So predict based on PI. So you put your hidden layer to the softmax to predict your next word, and each hidden layer PI is derived from your previous hidden layer and your previous word, obviously. So you have previous hidden layer, you have previous hidden layer going in, and your current previous word going in, and then you're trying to predict the next word as two, right? So a simple RNN here, and yeah, WE is word embedding. It's a lookup table. Interestingly, the first input to the LSTM is the image embedding itself. So they don't do a hidden layer initialization of the RNN with the image embedding. You could think of, you would imagine that would be the case. For example, if you think about sequence to sequence translation models, for example, if you're doing like English to French translation, you would put your English representation vector as the initialization of your French decoder. So that would be the case. But here, they're actually doing something different. They're using their image embedding as an input to the LSTM, interestingly. And then you have your start token and the end token. Right, so yeah, here, image embedding is fed into LSTM at time -1. And yeah, it's not used to initialize LSTM hidden vector. So hidden layers are probably initialized to 0, or like there are some hidden details. And interestingly, pre-trained word embeddings didn't really help. For example, word to vec. There was no BERT back then, so it was either word to vec or glove. So, and they try to use it at here, WE, which is the lookup embedding. So they could have initialized the WE matrix with the word to vec vectors, but it didn't really help. Beam search used in with beam size 20, trained in NLL, negative low likelihood. So you can think about how easy it is in today's standards. You can probably code it in like less than, I don't know, 50 lines or so, maybe 30 lines. And the popular data set back then was, so there was a very kind of a small scale that's called Pascal Vogt, and the MS CoCa was still there back then. So, and MS CoCa is still a pretty heavily used data set. So using these data sets, they actually showed better performance than human already. Like human performance was like 21.4, 21.7, 25.2, 85.4 on MS CoCa. Neural image caption generator, NIC, showed like better performance. So even that back then, it was already a pretty doable task, even with a very simple architecture as like Inception version 1 and LSTM. And you can see some examples here. So we've seen these examples. These are all like good ones. These are all good ones. You can see that described without errors. These are like okay ones. So some minor errors. You can see like two dogs playing in the grass, but there are actually 3 dogs. So this is, I mean, counting is always a complex task for neural models. So you can think of like you can like understand, and somewhat related to, so captions that are somewhat related to image but a bit off. So you can see here the guy is actually riding a bicycle, but it says it's a skateboarder does a trick on a ramp. So I mean, it is confusing. I mean, the context is everything is there. There's a ramp, there's like a guy with a helmet, and there's the guy is doing a trick like jumping. So you can easily get confused whether the guy is doing a bicycle trick or a skateboarding trick. And girl in a pink hat blowing bubbles. Well, there are no bubbles, but there is a pink hat, and maybe the model got confused because the texture was like kind of bubbly here. And the final one, complete error, completely unrelated to the image. You can see that dog is jumping to catch a frisbee. There is a dog, probably, but there's no frisbee, the dog, and neither the dog is jumping. So yeah, these are all kind of today's standards preliminary, but back then in 2015, these were like the state of the arts. Right. So the next one, right after show and tell, came show, attend, and tell, and you can imagine what was added to show and tell is obviously the attention mechanism, right? So show, attend, and tell, neural image caption generation with visual attention back in 2015, and mixing attention mechanisms with image captioning. So you can see there's like an obvious, like it's a natural fit. You're trying to look at an image and then write a caption. So there should be an attention mechanism on top of the image encoding process, right? So this is the high-level architecture. There's an image, and then you put your image into an encoder. It could be an Inception model, it could be an VGGNet, it could be some whatever resonant. And at somewhere in the intermediate layer, there should be a 14 by 14 feature map. So in the previous show and tell architecture, your final image representation, a single vector was fed into the LSTM. So you can see 512 image size and RNN size. So the image was actually, the output of CNN is also 512 dimensional. So you have only one embedding fixed size vector that represents the entire image. But in the show, attend, and tell, you're actually using a feature map. So in the intermediate layers, like 14 by 14 by like 14 by 14 by 512 or something. So you have the spatial information alive in your feature maps, and then you're trying to apply attention mechanism on top of that. So there's an LSTM that generates a caption, all the while attending on the feature maps at the same time. So, and at each time you generate a word like a bird flying over, like you would generate a word in a sequential manner, obviously, one word at a time. And each time the decoder generates a model. The decoder generates a word. It needs to attend to the image and then do a convex sum, like a convex combination of the image features. So you'll see what I mean. So example of bird flying over a body of water. This is what we want. This is the output from this image. So this image, given this image, the model is generating this caption here, a bird flying over a body of water. And you can see that actually the model is doing a pretty good job at attending to the relevant places. So a bird, when the model is generating the word bird, it is attending to, you can see the highlight here, the bird, and then flying over a body of water. So when the model is generating the word water, it is no longer attending to the bird, but actually the ocean, the sea in the background. So you can see it kind of knows what's happening. And in the original show attendant tell, there were two modes of attention. There was a soft attention. So you can see this is the soft, the top row is the soft attention, and the bottom row is the hard attention. So you can see that the model is only attending to one like image fiber or feature map at a time. So there's like a constraint. Right. So if you remember the encoder decoder architecture, when you were doing like French English translation, there was a French encoder. So this is your French encoder, and then this is your English decoder, right? English decoder. And every single time you generate one English word, every time you generate one English word, what you need is your previous hidden layer, S1, and your previous predicted word, previous English word, and the context vector, which comes from a convex sum of your hidden layers from the encoder, right? So you need three things: S1 previous, S1, C2, Y1 for generating Y2. So if you remember this detail from the sequence to sequence class, you can just automatically extend it to the image captioning task as well. So what we need in the encoder decoder architecture, what we need for attention-based image encoder, image captioning, we need an encoder to obtain image representation. So probably this could be this could be like CNN. Decoder to generate captions. So this could be RNN. So these two were already there in the show and tell in the previous work. And then what we need is a additional attention module to calculate the attention weights among the image features. So we only need one more thing. This is the only thing that is added to the previous work. And not surprisingly, you can use MLP to calculate the attention module. So back in, if you remember, the sequence to sequence class, the attention was generated, the attention weights were calculated by a feed-forward neural network, right? By taking in hidden layers from both the encoder and the decoder, right? So if you remember the detail, then we can use the same principle here. We can use a single MLP that takes in the image features and the decoder hidden layer to see the affinity or compatibility between the two, and then calculate the attention weights, right? So as an encoder, image encoder, they use Oxford VGGNet. So I think this was before, could be even before like inception. I'm not really sure. No, actually it's after inception. It's just that not really sure why they use VGGNet. And for the RNN, for the decoder, they use LSTM. Right. If you remember the convolutional process from like if we had 32 by 32 by 3 input, if you run a 5 by 5 by 3 filter on top of it, then you get 28 by 28, you get 24 by 24, and then so on and so forth. If you're not using the paddings, right? So this was the principle. And if you remember how receptive field can attend, like a single image feature or image fiber in the third layer can be attending to like this big receptive field in the input space, right? So please keep that in mind. So here, how to attend to a part of the image. So if you remember we haven't gotten into the detailed architecture of VG16, but it looks like this. There's the input, and then there's like a bunch of convolution pull, convolution pull, convolution pull, convolution pull, convolution pull, convolution pull, all the way. And then after that, they have a series of feed-forward neural networks, and then they have a softmax. Well, this would be the ImageNet classes, actually. ImageNet number of classes, 1,000. But before that, you had like 4,000, 4K feed-forward neural networks. So this was the original VG16 architecture. And in this particular work, the show attendant tell, they chose the output from this layer here. So this is like a 1, 2, 3, 4, 5, 6, 7, 8, 9, and ninth convolution layer. So in this, the output from this particular layer had a 14 by 14 by 512 feature map. So it would be like 1, 2, 3, 4, 5, 1, 2. Like this would be like 14, and this would be 14, and there would be like 512 channels. So it would be like a very long, cube. And if you so 14 by 14, that would be the spatial information, because your original input would be like 128 by 128 by 3. You had your original 128 by 120 spatial dimension, which shrunk down into 14 by 14. So you can imagine that each image fiber or image feature map in this 14 by 14 layer, in the 14 by 14 feature maps, it has a pretty big, receptive field, if you think about how it will be attending to like a large receptive field in the input space. And what they do is they flatten this 14 by 14 spatial dimension into 196. So 14 by 4, this is like 14 times 14 is 196, right? So right here. So instead of, so they actually kind of like, slightly destroy the feature, slightly destroy the dimension, spatial information by just flattening it to 196. So there are eventually 196 fibers, or not 196 feature maps, where each feature map is 512 dimensional. So that is what we have in this particular layer here. Right. And what they do is that, could you give me just a second, please? All right, sorry about that. So yeah, we know that what's happening in the image encoder output. So using that, we can extend, we can still apply the same principle of sequence to sequence in this case by doing this. So here's, you can remember what happened in the right here. It was encoder RNN, decoder RNN, right? Instead of doing that, we have encoder CNN, decoder RNN. But the principle is exactly the same. So the decoder, when generating a caption word, one word at a time, for example, here, if we're generating Y2, then what we need is H1, Y1 hat, and C2. And how is C2 calculated in this time? So how C2 is calculated this time is just simply using a attention weight that was calculated for each fiber. Each fiber has its own attention weight calculated from the MLP that we talked about. And then you just do a simple convex summation of that convex sum. So you can see that yeah, right here, a single attention or probability, you could think of attention probability, is assigned for each fiber or each feature map here, and then you do a softmax to make it into probability distribution, and then you do a summation over it, and then you get a final context vector which goes into here. And then the rest is exactly the same. You have your previous predicted word, your previous hidden layer from your decoder RNN, and then using these H1, C2, Y1, you mix them up in your RNN, and then you get H2, and then you use that to generate or predict your next word, Y2 hat. So the principle is exactly the same, right? So not so difficult, hopefully. And yeah, everything is trained in an end-to-end manner as well. There are some things that are like technical details. For example, like your RNN's hidden layer is it's not random, it's not randomly initialized, nor is it initialized to 0 vectors. It's actually learned. So they have another MLP that learns the initial state of your decoder hidden layer. And the way they do it is they use all the A's being the feature maps. So they use all the feature maps from your encoder output and then use that to initialize your hidden layer H0, for example. And they also tried, as I said, the authors also tried hard attention instead of soft attention. So instead of doing a convex combination of all these fibers here, they would choose only one fiber, one feature map, stochastically, and then use that to feed that into the decoder. So in order to do that, you need to do like a reinforcement learning to do that, because you're doing like a hard choice. Another thing that another detail is they encourage this, which means that they, out of all the, when generating all the words like Y1, Y2, Y3, all the way to like YT, they want the fibers. They want all the fibers to be used at least some amount, like at least, like, statistically to sum up to 1, which means that there's 1 here. So they want the fibers to at least be used in average, on average, at least once in the throughout the entire word generation, like the captioning process from Y1 to YT, so that all the like the entire image is like used in more fairly, or like the details are not missed. So yeah, there are some. These are the technical details, and you can see that immediately that using the attention mechanism immediately gives you like performance boost compared to a simple show and tell. You can see that it's happening from here to here. NIC being the neural image caption, show and tell. Here, not so much for this, but for CoCa, it is doing a pretty good job. Like here, you can see a big improvement in all different measures, and yeah, just by using one additional attention mechanism here. Some examples. So these are the correct attention examples. So here, this is the given image, and this is the given caption. A woman is throwing a frisbee in a park, and you can see that the frisbee. So what we're doing is where we want to see where the model is attending to for a given word. For example, in this word frisbee. So when this word frisbee is being generated by the decoder, we can see the attention distribution given to the image fibers, image feature maps. And you can see that at that point, this particular object, which indeed is the frisbee, is being attended to with the highest attention weight. So doing a pretty good job. A dog is standing on a hardwood floor, dog here, stop sign here, a girl sitting, girl here, group of people here, it's all working pretty good. So these are the correct attention examples. There are some obviously incorrect attention examples as well. I mean, even the caption is wrong. A large white bird standing in the forest, but this is not a bird. This, if you look at it, they are a pair of giraffes. But maybe to the VGGNet's eye, it looked like a bird with like a wing or something. And woman holding a clock in her hand, like this. This is actually a logo of some institution or something, or a sports team, but the model got confused with a clock. A man wearing a hat and a hat on a skateboard. I mean, none of this is true, and especially the skateboard, but it's a violin, but maybe the texture looks like a skateboard. So it's not perfect. Right, so these are the incorrect notation examples. And yeah, as you can see that one word, when you're generating one word at a time, how the attention distribution changes over the image fibers, image feature maps. And you can see that a woman, so A, when generating the first word A, weirdly, the attention is given here. Not really sure why. But when it's generating the word woman, it is actually attending to these two objects. And you can see that the throwing is actually, not sure if we're interpreting it to our own favor, but when you're generating the word throwing, attention is a bit given to here compared to woman, and the frisbee a bit focused to the frisbee itself, So, and the park, it has a pretty good idea. Like the park is everything except for the objects, the people, and the frisbee. So the forest and the grass is all catching up. It's all capturing pretty well. Right. So this is the end of the image captioning, and as I said, during this Thursday's practice session, you will be implementing show, attend, and tell. Any questions so far? I mean, if you follow the class very closely, it would be easy to see that these are just connecting or combining the components that we have studied so far, and then trying to mix them together, right? So it wouldn't be too difficult. Right, then moving on to text to image. So before it was image to text, so it was image captioning, but now it's text to image, which are a very big thing these days, especially with the advent of DALL-E 2 as Imagine and Stable Diffusion and that kind of stuff. But the history of text to image goes way back to 2016. So researcher named Scott Reed actually was one of the first people to do this kind of text to image synthesis, and using, obviously back in 2016 there was no transformer, there was no diffusion, it was GAN all the way. So it's text conditioned image generation with GAN, and these are some of the examples that was generated for the first time. And it knows the semantics, like small bird has a pink breast and crown and yada yada yada. And so it's obviously bird with pinkish or orange-ish chest. And you can see here the flower has petals that are bright pinkish purple, so you know that it at least looks like a flower with purple petal, right? So it knows what's going on. But you can, I mean, it's neither like high resolution nor the details are all alive. So compared to like recent DALL-E 2, this is a very preliminary work. All right, and the architecture is obviously very simple compared to today's standards. What you do is you encode your caption or your text using an RNN. So you would have a RNN hidden layer or a text representation vector, and then you concatenate your text representation vector or text embedding with a noise that you sample from uniform distribution or Gaussian distribution, because when you're using GAN, you always sample from a noise distribution, right? So you have your noise Z concatenated with your text embedding, and then you do an upconv or deconvolution to like higher dimension, and then that would be your generator. Discriminator would be the exact opposite. You have your generated image, and then you have your discriminator encoding your image and the caption at the same time, because it's a text conditioned image synthesis. It's not, you don't merely just evaluate whether your image is real or not. You need to also evaluate whether your image aligns well with your text condition, right? So that's where your RNN embedding, text embedding, also has a place in the discriminator network. So your discriminator network accepts both image and the text embedding at the same time, and then see whether it's 1 or 0. So the discriminator job is a bit complicated compared to simple GAN, whether you have just whether the image is real or not. Now it's two-dimensional. It's like image and text all at the same time. So the only case where your discriminator is supposed to predict 1 is when when the image is real and aligned with the text. So when there's an input real image going in, and the aligned text is given, then your discriminator predicts 1. All the other cases is all 0. Fake image, obviously 0. But real image with wrong text, also 0. Fake image with wrong text, obviously 0. So there are 4 different cases. And the authors of this paper, this paper, they only train their discriminator with 3 cases: real image right text, real image wrong text, fake image right text. Fake image with wrong text is too trivial, doesn't really have an impact. So they just excluded that, and then only trained their discriminator or the entire network with 3 cases. And these are the examples. So here, for example, this is the actual image and the actual text. So this is coming from the I think it's coming from the Oxford BERT dataset or San Diego BERT, UC San Diego BERT, some BERT dataset, right? And when given this text to the GAN generator, you can see that you can see that there are different variants of GANs, but I think this is one that they actually propose with some technical details, some tricks. But you can see that it looks like a blackbird, but it only looks like a blackbird. I mean, here it doesn't even look like a bird. Like this is not a bird. They are all not exactly a bird, but it has all the characteristics of a bird, even especially like crows or like some blackbirds. So it knows what's going on. It's that the details are not aligned. And it's the same deal with all the other examples here. For example, like they all look kind of like a bird, but they're not exact. They don't have the a complete perfect shape or textures or all the parts. So that was back in 2016 now. Right, there are some other examples, but I'm gonna just skip them. It's the same deal. It's the flower. Flowers seem to be easier than birds because you can see that there are pretty high quality flowers here, but these are not really, also kind of like missing details. Yeah, and before this was like all birds, this was all flowers. I think this is MS CoCa, and you can see that this is a way more complicated scene. So it's not doing a really good job. For example, a surfer doing like a surfing, it knows like the wave and ocean, and some like some things happening, like some things colliding into the wave, but again, the details are missing. But from far apart, it does look like it's doing a good job. Like all of this, like from very far away from the actual image, you can see that looks like a baseball, looks like a grass. I mean, looks like vegetables, looks like a food. So mainly because they're like low resolution images. This is like back in 2016. So they mainly dealt with like 32 by 32 or like 64 by 64, 120 by 128. So the missing details are kind of inevitable. Then like sometime like 4 years later or 5 years later, DALL-E 1 came along, and it was probably the most important thing that happened in the text to image synthesis field for a very long time, because it could generate like unseen, unreal things in a compositional manner. Because if you think about all these things here, these are captions that are these are the captions that are in the test set. Like all these captions are actual samples from the test set, so they're not out of distribution. The training distribution and the test distribution is almost the same. But if you think about what DALL-E 1 did, is they just trained their model on a lot of image and text pairs, and they completely went out of domain distribution. For example, they just made the model generate this kind of image, like avocado chair or daikon with tutu, walking a dog, or like a storefront with OpenAI, and you can guarantee that there are no images like this in the world. These are all completely imaginary, and this showed how well or how generalizable DALL-E 1 was back in 2021. So because you're just imagining things up, and then it's showing a very nice high quality images. So it was they didn't have any like GANs or VA. It was purely based on transformer, and only decoder only transformer. It was only decoder only. It was not sequence to sequence. It's like exactly like GPT 2 or 3. And they use something called vector quantization. So we're going to cover it right here. So they use like a combination of transform and vector quantization. And the models were pretty big. I mean, 64 layers, but it's not as big as GPT-3. And what is vector quantization? So in order to use transformer only to generate images, what they have is the overall architecture looks like this. There's only one gigantic transformer, and it's just decoder only. And you have your text embeddings, text tokens fed into like half of the transformer. This is all like text part. And then given the text, you want to generate images, one image token at a time. So what they do is they generate image in an autoregressive manner. In order to do that, you need to quantize your image into a sequence of codes, because images are just actually pixels. And if you try to generate images one pixel at a time, like I forgot the name. What was that? We talked about like VAE and GAN, and then some other like autoregressive model when we were talking about the VAE and GAN in the like 6th class or the 7th class. I forgot the name. It was does anybody have an idea? 그 픽셀 하나하나씩 만드는 모델 제가 얘기했었는데 6번째 클래스인가에서 이제 VAE 얘기하고 GAN 얘기하고 이제 오토리그레시브 얘기할 때 픽셀 CNN 죄송합니다. 맞네. 픽셀 CNN. 픽셀 CNN. 네. 픽스는 이제 그 이미지 채우는 쪽인 거고, 그것도 물론 이제 픽셀 단위로 하긴 하는데, yeah, it's Pixel CNN, right? So Pixel CNN. If you think about Pixel CNN, how it does is it generates one pixel at a time. So if you're trying to generate like 128 by 128, you need like 16,000 for loops, right? So that's not scalable. So when the OpenAI researchers, what they did is they didn't generate this part of the image. So this part is given, this part is text. So you have your text embeddings given, and then starting from this, they start generating one image unit at a time, not using image pixels because it would be too unscalable. It would be intractable. What they do is they use one image unit at a time. And the way they do it is they use something called vector quantization. So it's called VQ, VAE. So the idea behind VQVA is that you have an image encoder, image decoder. So it's an auto encoder. You have an image auto encoder based on either CNNs or vision transformers. So in the autoencoder, there's got to be some latent representation in the bottleneck part, right? So what they do is using the bottleneck part, they replace image fibers, image features, one image feature with one lookup embedding from there. So there's like a lookup embedding. So it's like this is like a word embedding or like subword embedding. They have a embedding. They have an image embedding for each image fiber or image feature in the latent space. So they swap that. They replace image feature with one embedding at a time. So that's how they that's how they discretize your image into a sequence of codes. So it's like this code. So this image is now, if you flatten it like in the show attendant tail, then this would be like image fiber number 512. Like 512, this could be like 10, 14, 135, 65, something like this. So it would be like a sequence of image codes. So yeah, an image can be represented as a sequence of tokens, just like text. So that's how they can put how they can feed text tokens here and image tokens here as a teacher forcing, and then try to predict and how to predict next image token one at a time in an autoregressive manner. So that's how DALL-E 1 works, with a lot of text image pairs, and that they had like a phenomenal generalization capability. But then after that, DALL-E 2 came along. But before we move on to DALL-E 2, we need to talk about something called CLIP, which is a very simple idea, but very, very fundamental, like foundational model that everybody uses these days. So CLIP comes from this paper called Learning Transformable Visual Models from NL, Natural Language Supervision, but everybody just calls it CLIP. It's another paper or great work from OpenAI from 2021. What they do is they just collect bunch of text image pairs, and they simply do contrastive learning using image and text encoder, and that's it. So this is all there is to it. There's text encoder, there's image encoder, and then you have bunch of bunch of text and bunch of images in your mini batch. Mini batch could be like 1,000 image text pairs or something. And then you have like how many, like n number of, you have, for example, let's say that your batch size is like n. So then you have n number of text representation vectors, basically text embeddings, n number of text embeddings from this text encoder. You have n number of image embeddings from this image encoder. This could be like CNN, could be VIT, whatever. Your text encoder could be like BERT or whatever. It could be anything. And then what you want to do is you want your paired image text on the diagonal line. You want their cosine similarity to be high, and you want all the other parts, their cosine similarity to be low, and that's it. That's all you do in this contrastive pre-training. And by doing so with very, very large amount of image text pairs, your text encoder, image encoder will be able to send your text and images into the same shared latent space, where the latent space is very well informed with the relationship between text and images. Like a dog, the text dog and an image of a dog would be in the same vicinity in the latent space, because they all give, I think they're sending that to like 1024 maybe, or 768, some shared dimensional space, by the way. And then by doing that, what they can do with CLIP pre-trained model is they can do some zero-shot testing, for example. Like given an image, you put that through your image encoder, the pre-trained image encoder, and you have your image. And what you do is you have a prompt that where you can swap your slot with some different objects in your text domain. For example, like it could be like a photo of a plane, photo of a car, a photo of a dog, a bird. You put that through your text encoder, and then you would have a embedding for a photo of an airplane, embedding for a photo of a car, embedding for a photo of dog. So this would be like, for example, this could be a photo of a dog. So this T3 embedding represents this text that went through this text encoder. And what they do with this is they calculate the cosine similarity between this your given image and your potential candidates, potential answers, and then select the one that is the highest cosine similarity. And that's how you do a zero-shot classification with CLIP. And obviously, if your CLIP model is well-informed, well-trained, then it'll do a very good job of selecting, the right T3, which would be a photo of a dog. There's a dog here, right? So they actually showed this actually worked really, really well, even though nothing is like fine-tuned or anything. It's just purely zero shot, but it does very well. It does almost as well as like a linear probing with a very heavily tuned resonant 50 model. So this became a very foundational model. A lot of people use clip embeddings to guide the GAN generation, guide the image generation using GAN to generate some specific style or specific objects. And yeah, they did a lot of stuff with CLIP. And after DALL-E 1, what the OpenAI researchers did is they used CLIP to build something called DALL-E 2, which is obviously the follow-up work, but DALL-E 2 has nothing in common with DALL-E 1. DALL-E 1 was based on transformer, purely decoder-based with vector quantization, but DALL-E 2 doesn't use vector quantization at all. It's purely based on CLIP and diffusion. So the paper is called hierarchical clip latence. But the essential idea is that they do text-to-image generation using clip priors. So we'll talk about the clip priors and classifier-free guided diffusion. Everybody knows. Hopefully, everybody knows what this is. Classifier-free guided diffusion. We talked about this in last week, actually, right? So how do they do this? How do they use clip to generate such a high quality image like these? Like this is beyond, this is not even compared to, like, DALL-E 1 doesn't even come close to DALL-E 2 in terms of the resolution of the image, the compositionality, the semantics, the style. Everything is just unmatched. So DALL-E 2 is like way ahead of DALL-E 1. So how does it work? So what they do is they have a pre-trained clip, because this is OpenAI, so they have their own clip lying around, right? So they have clip, and what they do is if you want to generate an image of this, a corgi playing a flame-throwing trumpet. So this is given as a text input. You put that through your clip text encoder. Then you have your clip embedding, clip text embedding, and there should be somewhere. I mean, for example, I mean, if you had access to this image and this text, you would have, for example, in your training samples of your clip training samples, if you had already had a text like this and an image like this, then what you can do is you can just simply feed this image into your diffusion model as a classifier-free guidance condition, right? So you can do that. For example, if you wanted to generate an image according to this text, and you knew there was already an image that looks like this, then you can feed this image into your diffusion model classifier-free guidance style. But that's not always the case, because you don't always have a image that corresponds to this. If you had this, you wouldn't even need to actually generate a synthesized image, right? What you want to do is you want to give any text into the model, and then you want the model to generate based on that text. So that what they do is you have your image, you have your one desired text put through clip embedding. So you have your clip text embedding, and then what you do is you know that your clip is so well informed of the relationship between your text and image. So what you want to do is you want to find, or you want to generate a clip. So this is your clip text embedding, which is given to you. You have your text, you put it through your clip, pre-trained clip text embedder, then you have your clip text embedding. And what you want to do is you want to generate a clip image embedding based on this text, Actually, before that, you could obviously think, hey, why don't we just put this clip text embedding into the diffusion model directly as a classifier-free guidance condition? You can actually do that. You can actually put your clip text embedding into your diffusion model and then train your diffusion model classifier-free guidance style to generate an image. And actually, that kind of works. It actually works pretty okay, but that the image diversity or the image semantic alignment is not really high, like, state of the art. So OpenAI researchers did a lot of different things, trying to put different things as a condition to the classifier-free guidance diffusion model. They just put real raw text into the model and see what happened. They put their text into the clip embedding and then obtain the clip text embedding, put that into the diffusion model, see what happened, and both were not 100% satisfactory. So what they did is you have your clip text embedding. You can generate clip image embedding using another diffusion. So you have your two diffusions. You have your diffusion that generates clip image embedding, and you have your diffusion that actually generates image itself, right? So that's where the clip prior comes in. You're using your clip text embedding, and then using that as a condition, you're generating clip image embedding in the latent space because there should be like a shared latent space in the clip embedding, right? So in this shared latent space, you generate clip image embedding using this clip text embedding as a condition, and then feed that clip image embedding into the diffusion along with clip text embedding at the same time as a classifier-free guidance. So that's how DALL-E 2 works. And you can see that there's actually two routes of generating. So this is where you generate clip image embedding given clip text embedding. And you can see there's two routes. There's route 1 and route 2, and route 2 is using the diffusion to generate clip image embedding, but they actually tried using autoregressive style as well. You can autoregressively generate one dimension at a time of your clip image embedding. You can also do that, and OpenAI researchers actually did that, and they both performed okay, but they just went with diffusion prior model, which showed us a little bit better performance, right? So that's how DALL-E 2 works, if that makes sense to you guys. Right. Any question? 그러니까 이제 혹시 몰라서 한국말 한 번만 더 하자면은, 우리가 이제 디퓨전을 배웠으니까 DALL-E 2가 어떻게 돌아가는지를 하이 레벨로는 이해를 할 수가 있기 때문에 이제 그걸 굳이 제가 이제 얘기를 하는 건데, 그러니까 우리가 원하는 거는 이제 텍스트를 주면은 이제 디퓨전을 이용해서 어떻게든 간에 이미지를 만드는 건데, 텍스트를 바로 텍스트를 이제 예를 들어서 이거를 버트 같은 데 넣고 이제 이거를 CLS를 뽑아가지고 그 CLS를 이제 디퓨전에다가 넣고 그 클래시파이어 프리 가이던스 해가지고 학습 이제 이미지를 만들 수도 있고요. 그것도 당연히 가능합니다. 그것도 되고, 그게 아니면은 이미 얘네들은 오픈AI는 클립이 있기 때문에 클립의 텍스트 인베더에다가 텍스트 넣고 클립 텍스트 인베딩 뽑아서 그 클립 텍스트 인베딩을 바로 디퓨전에다가 넣고 그 다음에 클래시파이어 프리 가이던스 스타일로 디퓨전 이제 이미지를 만드는 것도 가능하고요. 그래서 둘 다 해봤대요. 둘 다 해보고 이것도 해봤는데 둘 다 이제 어느 정도 되긴 하는데 이제 이렇게 세만틱 이제 개를 그리려고 했는데 사람을 그린다던가, 아니면 개를 그리려고 했는데 개가 막 구석에 가 있다던가 가운데 안 있고 이런 식으로 이제 약간씩 마음에 안 드는 게 있어서 이제 얘네들이 한 게 뭐냐면은 이 클립이 이미 있으니까 클립에 이미지 인베딩 어떻게든 쓰고 싶다. 근데 나한테 있는 게 텍스트밖에 없는데 어떻게 클립 텍스트 인베딩을 가지고 클립 이미지 인베딩을 만들 거냐 라는 이제 질문이 있잖아요. 펀더멘탈 질문이 있잖아요. 그거를 얘네들이 이제 오토리시브하게 만들어 보기도 하고 디퓨전을 만들어 보기도 해요. 그러니까 이제 디퓨전이 사실 이미지 만드는 거라고 생각을 하실 수 있는데, 디퓨전은 그냥 어떤 그 노이즈에서 내가 원하는 디스트리뷰션인 P 데이터를 뽑는 그냥 방법일 뿐이거든요. 그냥 제너레이션 방법이에요. 그러니까 VA도 그렇고 겐도 그렇고 디퓨전도 그렇고 내가 이제 알고 있는 보통 이제 N01이겠죠. N0i인데 내가 알고 있는 어떤 노이즈에서 데이터 샘플을 뽑아서 그거를 내가 알고 있는 원하는 P 데이터 디스트리뷰션으로 보내는 일을 하는 게 디퓨전이잖아요. 그렇기 때문에 여기서도 클립 텍스트 인베딩을 컨디션을 넣고 이거랑 상응하는 클립 이미지 인베딩을 얘네들이 같은 이제 레이턴 스페이스인 Z에서 살고 있잖아요. 이 클립이 여기서 찾는 거를 할 수 있는 거니까 이 클립 클립 텍스트 임베딩하고 가장 상응하는 클립 이미지 임베딩이 이 이미지 이 레이턴 스페이스에 어디 있는지를 이 디퓨전으로 이제 생성할 수가 있거든요. 그래서 그거를 생성해서 그거를 갖다가 이제 디퓨전에 넣어서 하면은 이제 아주 하이 퀄리티 이미지가 나오더라라는 게 이제 얘들이 하는 얘기입니다. 그래서 이게 이름이 하이어키컬인 거, 하이어키컬. 이제 이 클립 스페이스에서 한번 디퓨전하고 그다음 거기서 뽑은 클립 텍스트, 클립 이미지 임베딩으로 다시 실제 이미지 또 디퓨전하고 해서 두 번에 걸쳐서 이 디퓨전을 합니다. 얘네들. 물론 이거 외에도 정말 정말 많은 디테일들이 있는데 그건 이제 궁금하시면 이 페이퍼를 읽어보시면 되고요. 그리고 이제 이거랑 비슷한 게 많이 나왔죠. 뭐 이마젠도 나오고 이제 스테이블 디퓨전도 나오는데 다 조금씩 다릅니다. 그러니까 이제 어떤 거는 이미지를 바로 디퓨전하는 게 아니라 이미지를 또 오토 인코딩해서 그 오토 인코딩 스페이스 내에서 디퓨전한 다음에 그거를 디코더로 보내서 이미지를 만들기도 하고 뭐 어떤 건 이제 뭐 당연히 구글 같은 경우는 T5나 버트가 있으니까 그런 걸 이용해서 텍스트 임베딩 하기도 하고 클립을 쓰지 않고요. 뭐 하여튼 다 베리에이션들이 있는데 네, 뭐 어쨌든 핵심 그 원칙은 다 비슷합니다. 아, 그리고 여기서 이제 얘기가 있는데, yeah, I forgot to talk about this two-step upsampling. So what they do in diffusion is they actually generate 64 by 64 by 3 image in their original in this two-step process here. So, but what they do is they eventually generate 1024 by 1024 image, a very high resolution image. Then the way they do it is they first generate 64 by 64, 64 by 64. They super sample it to 256, 256. And then they super sample it to 1024, 1024. So there's like upsampling, upsampling, diffusion here. And there's another upsampling diffusion here. So in total, there's like 4 diffusion. There's prior diffusion, initial diffusion, upsampling diffusion. So there are 4 diffusion models at work here. 네, 혹시 여기까지 질문 있으신가요? 네, 사실 요즘 이제 뭐 당연히 달리2나 오픈 소스가 안 돼 있는 걸로 알고 있는데 스테이블 디퓨전이 이제 아예 코드까지 다 공개돼 있잖아요. 그러니까 이제 궁금하신 분들은 뭐 스테이블 디퓨전의 코드를 보시면서 이제 그 디테일들 하나씩 파악을 해보시는 것도 도움이 될 것 같습니다. Right, we're going to move on to the last subsection, which is image text multimodal pre-training. This has been a big wave as well for since 2019, I guess. So image text multimodal pre-training, very active since 2019, sparked by some initial works such as VL-BERT, ViLBERT, InterBERT, LXMERT. Like these, I think VL-BERT and ViLBERT were the very first ones to actually try this, and then came along a lot of different variants with different architectures, different contributions, different methodologies, different angles, different objectives, but unified VLP, Pixel-BERT, CoCa, Flamingo, BIT version 3. So these are like very, very recent ones. Flamingo, CoCa, BIT version 3. These are like 2022 models. These are like 2020 models or 2021 models. The objective is to pre-train a model to understand the relationship between image and text. So this immediately will ring a bell. Like CLIP is exactly this. CLIP has exactly the same objective, which is to pre-train a model in the contrastive style to understand the relationship. But what separates these models from CLIP is that these are early fusion models. They're early fusion, meaning that in CLIP, you have your image encoder, you have your text encoder, image encoder, and you don't mix the two. Actually, it's a very separate two-stream process. There's stream 1, there's stream 2. You have your text embedding here, you have your image embedding here, and all you do is just calculate the cosine similarity between the two, and then try to maximize it, minimize it based on based on whether they're paired, they're actual pairs or not, right? So there's no like fusion process, or there's no like you're trying to like do an basically early fusion. But here in all these works are actually a bit more, well, except for maybe Flamingo. Flamingo is a bit different, but yeah, they have all different. They're like slightly different. They're all different works, like all different works. So they have different styles and different like architectures, but they're more early fusion style. They have a unified encoder, for example. They have unified encoder that takes in both image and text at the same time, or like compared to CLIP where there's separate image and separate text encoder. Some of the models here have just one model that takes in image and text at the same time without treating them differently. And there can be many, many downstream tests. There can be image retrieval, visual question answering, image caption, image generation. There could be a lot of different things. And the common strategy for multimodal pre-training is that first you need to extract image features from the image, right? You have an image, you need to put it through some encoder or some whatever to extract image features or pixel features. And there are 3 ways to do it. There's using pre-trained object detectors. So for example, you can use FastRCN or MaskRCN, which are object detection models. And you can use that on your image and then extract object embeddings and then feed them into your BERT or transformer model. These were, and another thing is just directly feed pixel feature maps. You can just put your image into a resident or whatever, and then you have your feature maps, and then you can feed that feature maps into your BERT or whatever. Or you can use VQVA to first quantize your image into a sequence of codes and then treat the sequence of codes and sequence of text at the same time and then feed them into BERT model, whatever. So there are different strategies. And yeah, feed the image features and text to BERT. Usually it's transformer model. It doesn't have to be BERT, but it's at least some transformer model. And then you optimize for some pre-training objective. You usually use mask language modeling or mask image prediction, image text alignment, a bunch of different. You can have a lot of different auxiliary tasks. So very first work was ViLBERT, and this was back in 2019 actually. So you have your image features that are extracted from object detection models, and then you have your paired text descriptions of that image, and then you put that into a single BERT model. And what you do is you just do mask language modeling. That's it. You have your language, you have your text part masked 15% of the time, and then try to guess the identity. For the image part, you can't do mask language modeling on images without based on pixel information. You need to have some kind of semantic information to predict based on masks, right? For example, if you mask out this, what are you going to predict anyway, right? You can't predict the identity. You can't predict the pixels. These days some people actually do predict pixels, but back in the day, nobody was predicting pixels, right? So what they did is they actually predicted the object detection class labels. So MLM for the language part and the class label prediction for the image part, and they have the alignment, not alignment, kind of like a next sentence prediction. The BERT, they have the aligned, not aligned, another like a high level task for mixing the two at the same time, mixing the image and the text at the same time. So that's ViLBERT, and then they did a bunch of different downstream tasks, and there are a lot of different variants like LXMERT. I'm just gonna skip them. LXMERT, there's VL-BERT, there's Uniter, there's Pixel-BERT, which is kind of different. So Pixel-BERT is kind of different from the previous like BERT-based models, because this actually uses this is the first model that didn't use object detection models. They actually fed image features from the ResNet directly into BERT, and then show that it actually still works okay without the off-the-shelf object detection models. So that's Pixel-BERT. So a lot of different works, and they all focus on usually the same thing. It's either image captioning or visual question answering, or some semantic visual text alignment task, or image retrieval, text retrieval, cross retrieval. There are bunch of different things you can do. Right, and then so this is a bit more recent works. These are all pre-2021. So this is CoCa is kind of a recent work, and still it's not so different. They have image encoder, they have a unimodal text encoder, and then they have multimodal text encoder. And you can see that the image encoder output, which could be a VIT model, then image features are fed into your text decoder, which could be like a transform decoder, in a cross-attention style. There's like an encoder decoder cross-attention in the original transformer, right? So cross-attention style, feed it, and then you do a captioning loss. So this model is all about captioning loss and contrast loss, and that's it. They only use 2 loss. They don't do any math language modeling or anything. It's kind of like special model for special models for captioning only. So, and they do have very good captioning quality. For example, like here, a hand holding a San Francisco 49ers football. A truck is reflected in a side mirror of a car. This wouldn't have been possible with show attendant tell, but in 2022, now the model with a lot of data and gigantic models, you can do a very high quality caption like this. Right, and the next one is Flamingo, which is also 2022. So I think both of these were maybe, at least this was presented in the 2022 in Europe a couple days ago. So Flamingo is kind of like GPT-3. It's also this is a work from DeepMind actually, and this is based on prompt few shot. This is for prompt-based few shot task for few shot, few shot inference. So what they do is this is also like this is also a multimodal model. So they have vision encoder, they have a text encoder. They have the text encoder and the vision encoder, or actually they have a. No, we're actually missing a text encoder somewhere. Right here. Okay, so here, text encoder here. Well, actually not text encoder. This is language model, so it's a text decoder. So they have vision encoder, which are very powerful, like VIT, like large or whatever. They have very large vision encoder, which are frozen. And then they have a very large language model, could be like, I don't know, PAM or T5, T0, some model with some language model with a decoding capabilities. And they freeze it. So using very powerful frozen model, what they do is they mix and they interleave image and text, in a sequence of image and text interleave style. So sometimes they give image and text at the same time. Sometimes they give two images two images in sequence, two texts in the sequence. I think it's better to just look at what they're trying to do here. So eventually what they don't want to do is you have image and you have another image, put that through your model, and then you have a text that is paired with this image, and then you have a text that is also paired with image, but incomplete, and you want your model to predict or fill the incomplete part, right? Which would be, this is a very serious cat. And if you do this kind of task in a lot of different combination, like one image, one text, or two images, two text, three images, three text, whatever, like, or one image, one text, another image, another text, like, there can be a lot of different combinations, right? So you do that for a very, very long time with a very large model, and you can do things like this. So you give two examples. It's just like GPT-3 prompting. You give two examples. An image and a corresponding text, another image, corresponding text, third image, this is, and then go. This is where your model should start sampling text like GPT-3. And surprisingly, it does work pretty well. This is a flamingo. They're found in the Caribbean, South America. Another example, image, text, image, text, image, text, answer. So there should be an answer here. Answer, R. So 이게 이제 아르레 밤이라는 그 고후가 그린 그림이겠죠. 네. 뭐 그런 식으로 이제 여기도 이미지 주고 텍스트, 이미지 주고 텍스트, 이미지 텍스트, 이미지 텍스트 한 다음에 나머지 채워라 했을 때 보면은 이제 이게 뭐냐, 이게 이제 이 아웃풋이 여기 있는 거 언더그라운드, 여기 있는 거는 컨그레스 애비뉴, 여기 있는 거는 그럼 뭐냐, 솔로몬. 그러니까 이제 알아챈다는 거죠. 그러니까 이제 이런 식으로 예전에는 거의 뭐 상상도 할 수 없었던 이 프롬프팅 제로, 이 퓨처 태스크를 이 플라밍고라는 모델을 통해서 할 수가 있다. 근데 이게 이제 중요한 거는 굉장히 강력한 LM과 이제 이미지 인코더들이 있다. 그래서 그걸 이제 잘 사용해서 섞어주면은 이런 식으로 이제 퓨처 태스크들을 할 수가 있다. 네. 그러니까 딱 태스크가 정해져 있지가 않죠. 내가 이때는 그냥 이미지 캡셔닝 하는 거잖아요. 그러니까 여기서는 이제 이미지 캡셔닝을 하는 건데, 여기서는 사실 이미지 캡셔닝 하는 게 아니라 이 이미지 안에 있는 텍스트가 뭔지를 물어보는 거잖아요. 이 텍스트가 뭐냐를 물어보는 건데, 근데 이제 그런 거 몇 개의 예제만 보여주면 얘가 이제 바로 그냥 알아들어 먹고 이제 이렇게 한다. 굉장히 이제 그 제너럴라이제이션 캐퍼빌리티가 굉장히 세다는 걸 아실 수가 있겠죠. 그리고 이것뿐만 아니라 이제 이런 뭐 단순한 뿐만 아니라 이제 이미지 기반의 대화도 가능합니다. 이런 식으로 이제 이미지가 이렇게 아이팟이라고 써 있는 뭐 사과가 있을 때 보시면은, so these are like future examples, but this is dialogue based on image, and this is also very interesting. So there's a image of an apple with iPod caption attached to it, and then what you do is you can ask this model Flamingo a bunch of questions. So for example, this is given as a query, and then the model says something. This is an apple with a sticker on it. What does the sticker say? That's the follow-up question. And the Flamingo Flamingo would obviously be taking this image and this question at the same time, or maybe even its output, like all these previous history is given as a context to the Flamingo model, decoder model. The model says, the sticker says iPod. Where's the model? Where is the photo taken? It looks like it's taken in a backyard. You think it's printed or handwritten? It looks like it's handwritten. Like the question answering capability or the dialogue capability is just phenomenal. It's just out of this world, you know. And how this is possible is just based on a lot of data with very powerful foundational models and a smart combination of cleverly combining them, and then using a lot of different kind of tasks, like auxiliary tasks, multitask, a lot of different pre-training tasks to make it familiar with, you know, this kind of, you know, prompting situation. So yeah, so this is where we are with the state-of-the-art image text multimodal pre-training models. Right, so this is it. I think we ended a little bit earlier than usual, so that's good. Any question before we end this class today? 네, 혹시 질문 있으시면 해주시고요. 아니면은 I'm gonna wait for 5 seconds. All right, I guess there are no more questions. So hopefully, I guess, so this is the end of the class. I won't be seeing you guys. So this Thursday, the Thursday practice will be conducted by the TA. So this is the official end of the class for this semester. Hope you guys learned something. Hope you guys learned a lot from this class. Maybe at least you guys picked up how to, you know, implement very simple foundational models, and then you're ready to do more advanced research. So hope it has been an instructive or educational semester for you. And thank you very much for attending. Hope you guys do a great job on project number 2. And please don't be late. Okay, don't be late. And follow the specs very, very carefully, because we have 300 people, and we don't want to take TA's time too much. All right. 네, 요 정도로 그러면 이제 이번 학기는 마무리를 하고, 영어로 얘기했듯이 이제 다들 뭔가 좀 하나씩 잘 배우셔서 이제 AI 리서치를 하시는데 도움이 되셨으면 좋겠고요. 말씀드렸던 대로 프로젝트 2를 잘 마무리하시고, 그다음에 늦지 마시고요. 그다음에 포맷 스펙 그대로 따라가지고 TA가 이제 너무 힘들지 않게 쉽게 이제 채점을 해서 여러분 모두가 해피할 수 있는 그런 상황을 좀 만들 수 있도록 도와주시면 좋겠습니다. 네, 그럼 그동안 이제 수고하셨고요. 네, 한 학기 동안 수고하셨습니다. 감사합니다. 네, 다들 고생하셨습니다. 네. 네, 감사합니다. Oh, by the way, if you have questions, you can still ask them on class, and I'll be there as well. All right. All right. Thank you, guys. Thank you, guys. Bye-bye. Thank you.